Our next presenter today is Ana Garcia Caraveo, a Ph.D. student in material science. Her presentation is on micromechanical materials testing for fusion energy. Please join me in welcoming Ana to the stage.
Thank you. Thank you, Karina, for the introduction, and thank you, everyone, for being here today. Have you ever imagined living in a world where carbon-free energy sources were available to everyone? Let's be honest. I think we all have. And you might wonder, but why are we not carbon-free now? Well, there are many answers to that question, but one promising solution is fusion energy. Fusion is nuclear energy, but it's not what we might think of as a common nuclear reactor. That is fission energy. Fusion is a different process. During fusion, small atoms merge, forming a plasma that creates tons of light and heat and charged particles. This is a reaction that powers stars, like our sun. So think of fusion as having a small sun inside a power reactor, sort of like this. But I want to show you how a real fusion reactor looks like. Impressive. I'm a material scientist that works with the materials that are being proposed to build these reactors, specifically the materials from the walls that are going to be facing the plasma from the fusion reaction. These walls are going to interact with a huge volume of atom size and charged particles that are going to hit it at really, really high speeds, over and over at a high temperature. So these walls are going to be under a lot of stress. And the main worry is what is going to happen with these reactors. We're going to build them, and what's going to happen after a few years of operation. We want to know if the walls are going to crack. So we need to test this material and know their mechanical properties. Usually, to know a material's properties or to test them, we perform large-scale mechanical tests. With this, we predict how will they perform before we build anything with it. But we still need to know what the plasma is going to do to this material, right? But we don't have a sun here on Earth to do that. In nuclear material science, we irradiate materials with charged particles. These help us to simulate what is going to happen to the material in an extreme environment, something like facing a very hot plasma. But the damage from these experiments is too shallow, typically 1 to 2 microns depth. This is 75 times smaller than the diameter of a single hair. This is where we use micromechanical testing. I'm working with a tungsten composite made of tungsten particles and nickel, and we have done 2 different tests. The first one is nano-indentation. With nano-indentation, we use a very sharp and nano-sized diamond tip. With this, we can calculate the hardness of the materials in the composite. We did this first with the material before irradiation. That is our reference. Then, we irradiate the material at a high temperature with 3 different conditions: helium ions, nickel ions, and then both at the same time. These are the results. As you can see, the tungsten hardness increased. And you might think, well, that's a good thing, but it's not. This means that the tungsten particles are getting damaged from the radiation, but to what extent? We need a second test. This is where we did a bending test. This test was done in the tungsten particles with the same conditions I mentioned before. These are the results. As you can see, before irradiation, the tungsten particles have a bigger fracture resistance or a higher fracture resistance. Then, after irradiation, the fracture resistance drops significantly. This means that it's easier to form a crack in these tungsten particles after irradiation. These are not the results that we were expecting, but that's research. The positive thing here is that Micromechanical testing has shown us to be a very powerful tool to get the mechanical properties of materials when they are exposed to extreme environments. There's still a ton of work to be done, but I can confidently say that we are closer to bring clean energy for everyone and ensure a cleaner future for generations to come. Thank you.
Thank you, Anna.